Hey, good morning, everyone, and welcome to our subject, structural design of steel and timber structures. So, for today, we will be continuing our discussion regarding the design of timber beams, but now particularly solving some examples focused more on the design part. No, so our lesson outline for today is, as I've said, we will just solve two design examples wherein we are expected to identify what is the most adequate section for the given condition ng beam, and then we will check whether this dimension satisfy the serviceability and strength requirements that we have discussed before. Okay, so at the end of the session, first outcome natin should be to be able to demonstrate the use of the table that we have discussed previously, which is the Philippine timber properties with regards to stress grid niya. We have three classes. We have 80%, 63%, and 50%. So we will try to demonstrate how to use that. And then to design a beam that will satisfy all the requirements that we talked about last meeting. Okay, so as a recall or recap, so in designing timber beams, we need to satisfy four requirements. For strength requirement, we need to satisfy the flexure and shear requirement, or flexure or bending requirement and shear requirement. And then for serviceability requirement, we need to satisfy the deflection and lateral stability requirement. Okay, so let's go back briefly dun sa formulas for each requirement. So for flexure, when we are talking about a rectangular section, we are allowed to use the formula for the bending stress, actual bending stress of 6 times the moment or maximum moment within the beam over the product of the base times the square, yung square ng depth natin. Wherein this pertains dun sa moment over our section modulus, or moment multiplied by the centroidal distance to the outermost fiber over the inertia of our section. So since we are considering rectangular sections lang for this discussion, we can use this formula. Okay, and we should always satisfy this, no, that our actual bending stress should be less than or equal the allowable bending stress that we have on the table that we discussed. Okay, then for shear requirements, we are trying to satisfy the shear requirement for parallel to grain. Okay, so for rectangular section, we are expected to follow this formula. We have 3V over 2BD, wherein we also need to satisfy that the actual shear that we will be calculated here will be less than or equal the allowable shear reflected on the table. Okay. Next is for deflection requirement. So for the allowable requirement or allowable deflection, it differs from case to case basis, or depending upon the requirement of the problem. So sometimes this limit are given L over 360, L over 240, or L over 180, wherein yung L natin is the length or yung span ng mismong joist natin or yung beam natin in millimeters. Okay? And then for the allowable maximum load, we can use this formula. No? So depending on the type of loading that we have, we can use this formula. So if it's a combination of one or two setup, let's say we have a uniformly distributed load and we have a load acting on center, or concentrated load acting on center, we can use these two formulas, the one for the uniformly distributed load plus the one for concentrated load, to consider the effect of both forces, the effect of the concentrated load and the effect of the uniformly distributed load on our maximum deflection of beam. Okay, so you just need to add them. So if different condition or your beam does not satisfy any of these conditions, you need to calculate your maximum moment and maximum shear using the methods that we have discussed from your previous semester, which is using structural theory uh, methods or using your shear and moment diagram to calculate for the maximum shear and maximum moment in the beam. Okay? And then last of the requirement is the lateral stability requirement. So this is required to check whether our beam is stable enough to resist side sway movement. Okay, so we have three cases depending on the value of your L over B or your length over your width B. Okay, so depending on the value, if it's less than 20, so it means that our beam is laterally supported, so we don't need any reduction of flexural strength, or we can use the beam as is. Okay, so our flexural capacity from the first equation is already satisfied. For case number two, if our value of L over B is within or between 20 and 40, we need to reduce our flexural strength. Why? Because our beam should be partially supported. So we need to lessen the flexural strength because the full strength or the full flexural capability of the beam cannot be utilized now because of our ratio. No, so we cannot assume the full extent of our flexural strength because during its lifespan, more or less, if this will be our case, um, it will not reach its capacity. So maybe 81st, just 80% of our flexural strength will be the maximum. And then if our design is good for a 90% flexural strength or a flexural strength lower than that, so our beam will fail eventually in flexure. So we need to satisfy or to reduce our flexural strength, and then we need to recheck our values or actual values used in the first equation. Okay, so we need to recheck our actual bending stress with the reduced value of the allowable flexural strength. Okay, and then this formula needs the value of k, which can be uh, used depending on the value on the table. Okay. And then last part is when our L over B is greater than 40, it means that we need to introduce bridging or blocking in our um, beam. Okay. So when introducing bridging, what happens is our clear span shortens. Kasi when we introduce bridging at midspan, so our span right now or our span for the beam will be half of the full length because there will be an additional support or additional resisting member at the midpoint, which will help our beam not move sideways. Okay, so yung length natin will be reduced in half. So you can put your bridging at the center or at third points, at fourth points. But you need to evaluate whether you need to forego with the 3 points or 4 points if it's more economical versus the adjusting of cross section. So if it will be more economical to adjust your section, so you need to adjust your section na lang um, and not use bridging anymore. But if you think you will be more economical when you introduce bridging or strut in your beams or within your beams, so you can use your bridging as a uh, additional member to help you resist the sway from the lateral loads. Okay, so these four requirements need to be satisfied in order to use the cross section or to say that the section is adequate. And then this is again our table wherein we will be referring our allowable capacities. Okay, so we have there the value for deflectional strength, the value for the modulus of elasticity, and the value for the shear strength. Okay, so we will refer to this one later once we start with our problem solving. Okay, so I think we can now start with our first one. So the first problem is an 80% stress grade guijo wood is used as a joist to support the following loadings in a residential house. So we have two loadings. We have dead load and live load. So for the dead load, we have a flooring or floor system and self-weight of the beam itself, of the joist itself, equal daw siya to 500 pascals. Okay? So 500 pascals is also equivalent to Newton per meter squared. Okay? So it's a pressure yan. No? Then we have ceiling load and ceiling joist, 250